start the afternoon session. The first speaker is Professor Lunchakorn Tannukij. The title is Thermodynamics of a Black Hole based on many statistics. Please.
Okay, so, good afternoon, right, in Korea, everyone. So, yeah, first of all, I'd like to thank you for giving me this very valuable opportunity for me to give a talk here. So, yeah, today I would like to, tell something about thermodynamics of black hole based on this specific statistics. We call it Renyi statistics. So, yep, right. Wait, why it's not working? Okay, right. So this is like the outline of my talk. So, well, for the very first parts, there will be like basic contents. Basically, it's about black holes, thermodynamic of black holes, and then the latter half of this talk will be about like our work, about promoting the thermodynamics of black hole, which obeys different statistics compared to the standard statistics, of which we know it as Gibbs-Boltzmann statistics. Yep. So instead of that, we'll be trying to use Renyi statistics, right? And we will see the consequences of that. Okay, so let's go. So so basically, you guys know already what black holes are. So I would like to say review again that black holes are like some kind of objects whose gravitational field is so intense. So basically, nothing can escape from it, even light. Now, we have like several kinds of black hole solution. For example, Schwarzschild solution, Weisner-Nordström solution, based on the same symmetry, which is spherical symmetry, but with different contents in the space-time. For example, this Weisner-Nordström is with electric charges. And if we include the cosmological constant into the picture, then we can obtain the Schwarzschild solution, which obeys spherical symmetry as well. Now, the black holes, all of them, they have this structure called event horizons. This event horizon marks the region where if anything falls into, then it cannot escape. Now, this has a very important meaning in terms of thermodynamics, because if you, for any hot object, they always radiate thermal radiation, which is in a form of electromagnetic waves, which is basically light. So, but black holes cannot allow anything to escape from even light. Now, if we take into account these properties, then it means, for example, in our everyday life, the standard case like a hot coffee, you always expect thermal radiation away from it in terms of, for example, infrared. But for a black hole, because no light can escape from it, that means there should be no thermal radiation. And according to our thermodynamic knowledge, then an object which has no thermal radiation, we can think of it as at a zero Kelvin temperature. So this means if we see black holes in our universe, then all of the black holes should be at absolute zero. But thanks to Stephen Hawking, he showed that black holes may have thermal radiation, So with his technique using quantum field theory on a curved space-time, he can show that there can be thermal radiation, the so-called Hawking radiation, which can be originated from quantum fluctuation around the event horizons. So there are debates on this kind of concept, but one of the interpretations is that this quantum fluctuation may happen around the event horizon, which can cause a pair of particles. To be more specific, it's like a particle and the antiparticle. The particle may escape away as a radiation, while the antiparticle will be absorbed into the black hole, and that would reduce the black hole's mass and energy. This picture, although it still contains some flaws, but in one way, it explains why a black hole may radiate some thermal radiation in the quantum aspects. And at the same time, the mass or the energy of it decreases as it radiates thermal radiation away from the black hole. So now with this kind of concept, Hawking showed that this thermal radiation, of course, it would be specific for a temperature. If you have a thermal radiation, of course, you can measure the temperature. And this temperature, the so-called Hawking temperature, is related to what we call surface gravity. The heavier the surface gravity, the more the temperature of the black hole. So in terms of SI unit, it is written in this form, but in this work, we prefer to work it in Planck units. We kind of set everything to be 1. So basically, we have this formula for the Hawking temperature, which is based on surface gravity. This surface gravity is specific for the radius of the event horizon as well, which means if you have different black holes of different sizes, then you can end up having different surface gravity as well. Now, the surface gravity can be evaluated if we are talking about the spherically symmetric solution, for example, Schwarzschild black hole or Rising-Nordstrom black hole, or even the Schwarzschild de Sitter black hole, then it can be easily evaluated from the metric function, which is obtained from the line element of that geometry. All right, then, so this is an example. So for the Schwarzschild metric, of which it will be in this form, you have this metric function here, 1 minus 2m over r, while m being the black hole mass. So of course, you can easily find the event horizon, which renders this metric function to be 0, which is 2m. So knowing these quantity, you can evaluate the surface gravity of the Schwarzschild black hole. So once we know the surface gravity of this black hole, then of course we can determine the Hawking temperature of the Schwarzschild black hole. Now, here is where the thermodynamics kicks in. So if we take a look at this Hawking temperature, T equals 1 over m, essentially. So if you are considering a black hole with a very large mass, then this means the temperature of it should be very small, right? So if somehow the mass of the black hole increases, this would tell you that the temperature of it drops. Now, this seems to be a little bit strange because if you consider again a cup of hot coffee, right? If you give it some energy, some thermal energy, which means you are inserting some bunch of thermal energy into this system, then of course the temperature should rise. The temperature should increase to some higher value, something like that. We know that for sure every time that we drink coffee. Now, this happens in the opposite way, where if you put in some mass into the black hole, which increases its mass, the temperature drops. According to this form of Hawking temperature, we can also determine the entropy of this black hole as well. Now, it will take this form. And this entropy of black hole is commonly known to obey what we usually call it area law, because you can always find a linear proportionality between the entropy and the area. So basically, it's just like A over 4 to be an entropy. Now, this property, this strange thermal property of the black hole can also be realized through computing the heat capacity of the black hole. Now, if we treat the mass m to be the internal energy of this thermal system we call the black hole, then we can find the heat capacity, which is just, we can just using this definition, the standard definition, and then we end up having a negative heat capacity. So this basically confirms that what we said before is like, it's true, because once you increase the mass, and somehow the temperature decreases, this relation becomes negative. So here's the negative side. Now, in this case, we can call this system unstable in terms of its thermodynamics. So this is what happens for the Schwarzschild black hole. And this situation, of course, it introduces the strange phenomena that I mentioned. Now, let's say if we have a black hole, let's say a Schwarzschild black hole, which sits in our universe, and we also know that our universe has its background temperature, the CMB, which is at a very low temperature. Now I forgot the value of it, but if we have a black hole which is a little bit colder than the surrounding, then this means there should be a thermal radiation from the background being transferred to the black hole, which makes the mass greater. But as the mass increases, the temperature of it decreases because of the negative heat capacity. This means as it gains more mass, the temperature decreases, and the difference in temperature between the black hole and the surrounding will be larger and larger, and that would that would make the process, these kind of process, even faster and faster until the black hole freezes at 0 Kelvin. Now, if we leave it, let's say if we have a black hole and if we leave it in a universe long enough, the black holes, any kind of black holes, will always be at 0 Kelvin. But on the other hand, if we have a black hole whose temperature is a little bit higher than the surrounding, then this would cause a transfer from black hole to the surrounding, which means the black hole will lose its mass, it will increase its temperature because of the negative heat capacity, and then the temperature difference between the black hole and the surrounding will be even greater and greater. It will speed up the process until the black hole heats up. As it heats up, the mass decreases. Now, this situation is what we usually know it in literature as black hole evaporation. So in one way, this may seem fine in some aspects. But if we take into account the standard thermodynamics as we know it, it may be a little bit strange because it behaves in the opposite way as what happens for hot coffee, for example. So this is like the starting point of our work. And also, if we take into account the cosmological constant of the universe, we know that our universe is expanding with acceleration. And this means, and one of the modules that can module, yes?
Could you explain this difference between the thermodynamically unstable Schwarzschild black hole and the dynamically stable Schwarzschild black hole?
Can you hear that question again?
So could you explain the difference thermodynamically unstable Schwarzschild black hole and the dynamically stable Schwarzschild black hole? There is a difference between the thermodynamic stability and the dynamical stability. Why?
Did you say dynamic stability?
Yeah, that is the usual stability analysis for existing the black hole in the curved space-time.
Okay, so let's say if a black hole is thermodynamically unstable, this basically means it has negative heat capacity. That's it.
Yeah, I know. Yeah. Then but the dynamically stable for the Schwarzschild black hole. Why there is a difference between the thermodynamics and the dynamical aspect?
What do you mean by the dynamic stability of a black hole?
Okay.
Sorry? Sorry, I can't hear you.
Okay.
Can I go on?
Yeah, please go ahead.
Okay. Sorry, we can discuss about this later if you want. Okay. All right. And yeah, of course, if we want to include the cosmological constant into the picture, then we can end up with a Schwarzschild-Sitter metric where the cosmological constant is included in the metric function. Now we can do everything again. We can do the same computation on this thing again. We can get the surface gravity of it. We can get the Hawking temperature of the Schwarzschild-Sitter again. So for some terminology, let me call this R plus a black hole horizon and RC the cosmological horizon. Now, because of this kind of a polynomial structure of this metric function, you can end up having two event horizons, which is the smaller one, we call it black hole horizon, and the larger one, we call it cosmological horizon, which is closely related to the value of the cosmological constant. That's why we call it the cosmological horizon. Now, one of the problem of this Schwarzschild-Sitter solution and its thermodynamics is that usually the thermodynamic quantities of black holes are very specific to the value of to the position of the event horizon. Now we have two. So which one we have to choose? That's the question. Now, in our work, we kind of use this as an assumption, which assumes that, of course, we have two event horizons, and if we try the previous mathematical computation on both of the horizons, we will end up having two values of temperatures. So we may treat these two temperatures as the temperatures of different thermal system. One at event horizon, one at black hole horizon, the other one at cosmological horizon. And we may assume that the distance between the two systems is large enough, which cause the thermal energy transfer between the two systems to be slow enough, which means if we take into account this system only, then if we consider this system in a very small time scale, then we may think of it as being thermal equilibrium, or to be more exact, like quasi-equilibrium. So basically, with this assumption, this system can be in thermal equilibrium in some certain amount of time, after which it may be out of the equilibrium, and we will not consider that case. So this means in order to compute all of the thermodynamic quantities, we may use the black hole horizon, the R+. And of course, we may compute everything again, the Hawking temperature of the Schwarzschild Sitter black hole, which is in this form. Now, in the range of interest, it yields the same consequences again. So basically, as the mass of the black hole increases, the temperature drops again, in the same way as the Schwarzschild black hole does. Yep. So this would inevitably lead to having a negative heat capacity, which I showed here in the last part here. So the entropy still obeys the area law. This is not so surprising. And then the heat capacity, of course, as I mentioned, it becomes negative again. So this means this black hole is thermodynamically unstable in terms of its thermodynamics again. So now, if we want to fix this, if we want to believe that black holes in our universe, the simplest one would be like the Schwarzschild Sitter black holes. If you want to believe that these are just thermal objects as we know it, so that means
question.
Yes.
So then, where can you define the Hawking temperature in the Schwarzschild space? Usually, the Hawking temperature is defined at the infinity for the Schwarzschild black hole, but this is not the. This system does not have an infinite asymptotic infinity. So then, how to define the Hawking temperature in the Schwarzschild space? This is not the local temperature, actually, because you just mentioned the temperature is the Hawking temperature. So it is not easy to define the temperature and the thermodynamics in the Schwarzschild space, because there is another horizon, like a Cosy horizon, but the space between the outer horizon and the Cosy horizon is not the finite, not the infinity. So therefore, the same approach to the Schwarzschild black hole is not suitable for the Schwarzschild case, actually.
Okay.
You are going with the same as the Schwarzschild case.
Yes, we did follow the same process that we did in the Schwarzschild case, right? I think there was a paper about this as well. In like they usually I forgot the name of the paper. They mention the way that we can efficiently define the Hawking temperature in this form, and is like we can at least find a place where the property around it is very close to the asymptotically flat space-time.
No.
Right?
That is not the correct approach to the Schwarzschild space, which has a two horizon. It's quite different, actually. Thermodynamics is different. If you define some thermodynamics in the Schwarzschild space according to the Schwarzschild case, but in this case, I mean the Schwarzschild case is you have some different picture for the thermodynamics and the thermodynamical quantity actually. It's not straightforward.
Okay. So you said that I cannot just define the Hawking temperature this way, right?
Yeah, you can define the Hawking temperature, but that temperature is the local temperature or the Hawking temperature, which is defined at the observer. Observer is located at the infinity observer, okay? Measure the maybe Hawking temperature of the black hole, but in this system, there is no asymptotically pressed space-time. So therefore, the original precise definition of Hawking temperature in the Schwarzschild space is maybe problematic actually.
Okay.
Yeah. Okay, please
Yep.
go ahead.
Okay, so let me continue then. But thank you for your valuable comment. Okay, so all right. So if we follow this formulation, then yes, of course, we will end up having negative heat capacity again. Now, so one of the properties that the Schwarzschild black hole and the Schwarzschild black hole is that they share the same property where the entropy is related to the area of the black hole itself, the so-called area law. So usually in the standard thermodynamics, the entropy is known to be the macroscopic quantity, which means it depends on the volume. If you double the volume, so you double the entropy. Yep. So this means this entropy, this form of entropy may not obey the standard form of addition. The composition rules of this entropy, let's say you have two systems, each of which has its own entropy, and then when you combine these two systems as one thermal object, you can just add entropies into one total entropy. But since this entropy has different properties, so you may not be able to use this composition rule. So if we cannot use this, then that means we may end up with some non-extensivity kind of property of thermal objects. So one of the composition rules that incorporates the non-extensive property is known as Salix composition rule. So if you have two thermal systems, then the first system S1, second system S2, and then when you want to find the total entropy, then you can just follow this formula, where this lambda here is known as non-extensive parameter. If this lambda is 0, then you end up with the usual composition rule that we usually use in thermodynamics. Now, our assumption is that if the entropy of black holes obeys this kind of rule, then what will happen? That's the question. Now, well, if you use this rule, then it may be a little bit difficult to define the zeroth law of thermodynamics, and that means it can also be difficult to find the first law of thermodynamics as well. So if we want to realize this composition rule in terms of the zeroth law of thermodynamics as we know it, then we may find a mathematical mapping of this Salix entropy into what we know as Renyi entropy following this formula. So if we have a entropy which obeys Salix composition rule, and then we mathematically transform it into SR, the Renyi entropy, then if you try to realize a composition rule for SR, you will see that the composition rule will be just an addition of the Renyi entropies of two systems. So our work is that we suppose that if our entropy obeys Salix composition rule, and then we mathematically map it with this formula into the corresponding Renyi entropy. So if we do this, then the thermodynamic quantities will change. So if we instead have this entropy, then instead of this form of Hawking temperature, we will end up having this with an extra term here. So where this lambda here tells you about non-extensivity kind of property of this system. So in one way, you can think of it as like it kind of naively behaves just like this term. So instead of negative sign here, you have positive sign here. So basically you can, but this is just a naively speaking. You can think of this non-extensivity parameter here as a negative of something that behaves just like cosmological constant. But this doesn't have any geometrical meaning in terms of general relativity. So now we have the Renyi entropy, which corresponds to a Schwarzschild de Sitter black hole. And if we try graphing it, then we can see that if we compare to the previous temperature of the Schwarzschild de Sitter black hole, which is in this orange line here, if we use the Renyi formulation of this temperature, then we can see the change here. So this is a bigger picture of it. Now we can see that there exist three kinds of regions. The first region here tells you that if the size of the black hole increases, the temperature drops. Now this is not so surprising because we saw this kind of property already in the previous situation. Now there is this region as well where if the size of the black hole increases, and of course the temperature drops again. But there exists this part in the middle. So this middle part here tells us that if the mass or if the black hole size increases, then the temperature increases. Now this is actually what we want in terms of the realization of thermodynamics of black holes. This is what we
Question.
Yes.
So how to choose the lambda in drawing this picture? Lambda. Yeah.
Okay.
Because the lambda dependence actually
Yes.
Renyi temperature is.
So I'm sorry that I forget the value of lambda here, but usually there is this critical value of lambda where below which you cannot find this property So that means in order to have this property here, then you have to choose the value of lambda, which is greater than this specific critical value of it. So, but the value of lambda here, it cannot be greater than 1. Where is it? Yeah. So you can choose something like 0.5, 0.6, depending on the model parameters in this case. Is that answering your question?
Okay.
Okay.
Yeah, I have one question. Can you go back
Yes.
to the Lunny entropy that you can, okay. I mean, so will you go back one more page? Salix?
Sorry?
Yeah, so will you go back one more page there? One more
page.
previous page. Yeah, here. Let's see. So here, I mean, basically, what are you considering? I mean, S1 and S2. You are considering the same. I mean, you just divide one black hole system into two, which is thermally, I mean, equilibrium, or you are considering initially remove two systems, 1 and 2, and then after merging, you are considering S total. What kind of system you are considering?
So what I considered is that
Yeah, well, I mean, what basically you are defining S1 and S2, which is non-interacting force?
So I'm sorry.
Yeah, I mean, usually in the thermodynamics, when you consider some composition law.
Okay, S1 is okay. Horizon. S2 is cosmological horizon, maybe.
No, no, I think he's different thing.
Well, you may. So what I'm talking about here is only one black hole, but our assumption is that if there were two black holes, and if these two black holes were to combine, then the S total would be calculated this way.
Okay, so basically you're assuming kind of a merging process from two black hole into one, right?
Right.
Okay, then will you go back to the next slide? Lunny entropy definition. Okay, here.
Yes.
So I mean, this property, I mean, composition property is valid for arbitrary value of lambda, or you need to consider this lambda region?
Well, mathematically speaking, the lambda can be within this range. So it can be less, it should be less than 1, but it can be as negative as it can, mathematically speaking, in order to have this formulation valid.
Okay.
But actually, in our work, we actually want to avoid a logarithm of some negative value. So basically, we limit this lower bound to be 0.
Okay. So you mean that I mean, if you consider this kind of region, this composition is low, valid for arbitrary value of lambda. That's what you are saying, right? Okay. Then the next question is, what about, I mean, first law? I think that if you, I mean, deform this entropy, you would have some different first law, or you define different, I mean, temperature, something like that, maybe, right?
Yeah. You can, if you use this entropy, this form of entropy, you can always end up with the first law as we know it, if we define the temperature which is suitable for that first law and the entropy, right? Well, because the entropy is like the conjugate variable of the temperature. So if the entropy is modified, then the temperature is also modified as well.
Okay, thank you.
Right. Thank you for the questions. Okay, so right, we have this region, and right, so this region means that we can have a positive heat capacity situation, which means it can lead us to a usual sense of thermal equilibrium with the surrounding. If we have a black hole with some certain temperature, then we can fit it in a surrounding with some specific temperature, and then these two may be able to be in thermal equilibrium. Okay, so this is the heat capacity in Renyi statistics. So this graph ensures that this region, the middle region here, gives the positive heat capacity, while the other two regions result in a negative heat capacity kind of thing. Right. So yeah. Right. So right here, where the size of the black hole is not too large or too small, then you can end up with black holes as thermal systems, which obeys your thermodynamic intuition. Right. Okay. So
yeah, I'm sorry.
Yes.
So yeah,
Please.
Here, I mean, basically, where is the cosmological horizon? So I think Professor Yun-Sun Young, I mean, mentioned about the cosmological horizon when lambda is positive. So here, I mean, there should be cosmological horizon other than the black hole event horizon. So where is it here?
Oh, yes, of course, there should be. Well, this is all. How to say? So this is only the graph between the black hole horizon and the temperature. So the cosmological horizon is somehow hidden in these parameters actually. So right now I don't have the solid answer for you, because it's like a very complicated formulation actually. But
right here, I think the 1 minus lambda r square factor, that's the zero when the cosmological horizon. So you are considering more or less somewhere in between, right? But my question is that there is no meaning. I mean, there is no meaning to consider horizon beyond the cosmological horizon. So I don't know why you consider this kind of whole region.
Yes, you are right actually. So this is just I mean, like when I graph it, I just graph it I just graph it on and on. Okay. So yeah, when I graphed it, I didn't consider the position of the cosmological constant, but you were right. You were right already. You were actually right. So we cannot consider anything beyond the cosmological horizon. Yes. And if I am correct, the cosmological horizon should be somewhere around 7. I'm not sure. I need to check. I need to check this again. Right. Okay. So yeah, that's it for my talk. Yep. So basically, my message here is that the black holes, if we want to treat black holes as like thermal objects, one alternative way to consider it is maybe to leave from the Gibbs-Boltzmann statistics, of which we usually use in standard thermodynamics, but we may try Renyi statistics and try this with the black holes as thermal systems. So with this kind of language, I can show you that, as I showed you already, that it can be thermodynamically stable. Right. Thank you. And questions and comments are welcome. Yep.
Thank you. Any question or comment?
Okay, I have comment. You have time? We have enough time to discuss?
4 minutes.
Okay, so this is a comment on your works. So actually, it is very delicate and non-trivial issue to define the thermodynamics between the event horizon and the cosmological horizon. You just isolate the event horizon as a quasi, but that is not the correct way to define the black hole in the cosmological horizon actually. So if we consider maybe the stability issue, if you go to the inside across the inner horizon, I mean that the cosmological horizon, there is always blue shift. That means that the cosmological horizon is unstable in compared with the outer horizon actually. So so the two system is here. Schwarzschild case, you have to be careful to deal with the thermodynamics of this system actually. This is comment.
Right. Thank you.
Any other question?
Can I ask a question?
Yes.
I think here the cosmological constant is not the main issue, right? So even if you consider less space, you can define your entropy and temperature, right?
Yes, of course.
Okay. But I think, so anyway, so if you accept your definition of entropy, then even if you consider merging process of the two black holes, the entropy is always the same, right? Not increasing. Right. So I don't know, how to, so usually the second law, which is the equal or greater than the sum of the two entropies. Because of that, we can define temperature and entropy. So I don't know how to, say the situation.
Sorry, what was your question again?
How can we understand, whether this kind of system is really somehow because of your entropy is always the same. So actually, your entropy may not be, the real entropy because it is always the same. It is always something like equilibrium.
Yeah, to be honest, we may never know right now. So this kind of results, or even if we try this with quantum black hole, then right, we may never know if this is a true entropy or not unless we have an observational data. That's what I believe. So right now, it's just like trials and errors, to be honest, to admit to you honestly.
Okay, thank you.
Thank you.
Okay, thank you. Let's thank the speaker again.
Right, thank you.